First thing that we are going to talk about today is the Cascode BJT stage. So I would like for you guys to consider the following two BJT current sources as shown below here. So on the left, I have an NPN current source where here's an emitter to generation resistor RE. This is my collector, base, and emitter. And here is our output resistance, R out. And over here on the right, I'm going to draw the PNP representation of the same circuit. So here's my emitter to generation resistor, RE. Here's my voltage. And we have collector, base, and emitter. All right. So based on the results of the analysis we did in 335, in either case, doesn't matter whether it's a PNP-based current source or an NPN-based current source, we should observe that we get an output resistance of R out is equal to 1 plus GM RE in parallel with R pi multiplied by R naught plus RE in parallel with R pi so if we have a simple BJT current source like so, here's the bias, here's R out. Let's say that IC is equal to 1 milliamp and VA is equal to 5 volts. Let's determine the output resistance of this configuration with beta is equal to 100. And then we're going to repeat it with a generation resistance RE of 100 ohms. Okay. So we're effectively looking at what the purpose of this degeneration resistance is. So without degeneration, we have a simple resistance of R naught, right? Where for a BJT, R naught is given as VA over IC, which is 5 volts over 1 milliamp, or 5 kilo ohms. And this is exactly equal to R. With the emitter to generation resistor included, we need to know what our transconductance is, GM, where GM is IC over VT, and we need R pi, which is given as beta VT over IC. So from this, we get an output resistance of, so let's see, 1 plus IC over VT multiplied by RE beta VT over IC over RE plus beta VT over IC. All of this times 5 kiloohms plus that RE in parallel with R pi term again. Which should come out to be, sorry, go away thing, 23.615 kiloohms. Okay. So this degeneration resistor is fulfilling a very important role here. The 100 ohm resistance causes the output resistance to increase by a factor of almost 5-fold. All right. So we go from an output resistance of 5 kiloohms to an output resistance of 23.6 kiloohms. Okay. The principal drawback of this resistor degeneration scheme is the reduction in headroom seen at the output. And so what that means is that this resistor RE will have an associated voltage drop over it, which depends on the collector current, IC, right? Since we have to maintain a certain value of VCE in order to keep our device in saturation, this can be problematic. So to reduce this trade-off in headroom versus output resistance, engineers have developed a technique called cascoding, in which an additional transistor is placed in the signal path. So what that might look like is this guy. So let's call this V bias 1. This will be Q1. This will be Q2. And we'll call this bias voltage V bias 2 when we're looking in through the output terminal. This is effectively the same as this circuit. Where we're replacing transistor Q2 with its output resistance R02. And we can follow a very similar path for PNP transistors. Here's Q1, here's Q2, V bias 2, V bias 1, like so. Here's Q1, and here is V bias 1. Okay. So this process, known as cascoding transistor Q1, introduces a large small signal impedance, R02, to the emitter of Q1 while consuming a headroom that is independent of the current IC1, or our collector currents, okay? So in a cascode configuration, our output resistance, and this is literally directly from our previous output resistance with a simple emitter degeneration resistor, is given by 1 plus GM1 R02 in parallel with R pi 1 times R01 plus R02 in parallel with R pi 1, which is approximately GM1 R01 R02 in parallel with R pi 2 when GM1 R02 in parallel with R pi 1 is much greater than 1. So if we repeat our previous example, with a cascoded transistor, so let's say, sorry, that went slightly too far. We have the following circuit. Here's V bias 2. Here's V bias 1. Here's our base 1, collector 1, emitter 1, collector 2, base 2, 2. This is what we're trying to find, R out. And we are given IC1 is equal to IC2 is 1 milliamp. Beta 1 is equal to beta 2 is equal to 100. And VA1 is equal to VA2 is equal to 5 volts. So that effectively we're just cascoding this one up with an identical transistor as to what we used in our previous example. What we'll find is that our output resistance R out is IC over VT times VA over IC times VA over IC times beta VT over IC divided by VA IC plus beta VT over IC. And substituting in these results, we get a resistance of 328.9 kiloohms, which is roughly 1,300% greater than degenerating by a simple resistor, and about 6,500% greater than no degeneration whatsoever. Okay. So this cascoding here, one of the biggest advantages of it is that we get extraordinarily large output resistances by doing this. That is exactly correct. We use this to increase gain. Increase gain, and it's got a lower hit on headroom. Okay. So as R02 goes towards infinity, so I'm going to write this down. As R02 approaches infinity, R out goes to GM1, R pi 1, R naught 1, or beta times R naught 1. And this gives us the maximum possible output resistance we could ever see. So effectively, if we were biasing our circuit with an ideal current source, right? So if we had this configuration, this I ideal, here's our bias voltage, V bias 1, here's our output resistance, R out. This is the same. We're going to have a small signal model like this. Sorry, VBE. Here's R naught 1. Here's our base, collector, and emitter terminals. And here is where we're looking in for R out. And we would observe that R out is equal to GM1, R naught 1, R pi 1, plus R naught 1, plus R pi 1, which is effectively beta times R naught 1. So this gives us the fundamental maximum output resistance that we could ever hope to achieve with a BJT-based current source. And it's because we have to include the internal resistances of the BJT itself, right? So we can never hit an infinite output resistance. So what is the maximum output resistance for the circuit that we've been dealing with, our simple BJT current source degenerated by an ideal current source, right? So if, all right, so how does the output impedance calculated previously compare to the theoretical maximum value of R out? Okay. So R out max is beta VA over IC, which is 500 kilo ohms, right? So when we had no degeneration whatsoever, we were effectively at 1% of the maximum value, right? We're doing a pretty crappy job. when we had degenerated by a 100 ohm resistance, our output resistance was in the ballpark of 25 kilo ohms, right? So 25 kilo ohms would be about 1/20th of this. So somewhere close to 5%. So better, but still not particularly close to its max. Now, if when we had done a cascode configuration with VA was equal to 5 volts, we got 328 kilo ohms, which is about 66, 67%. So significantly better. If we had chosen a transistor with a higher early voltage VA, what do you think would happen? Exactly right. If VA is larger, then R naughts get larger as well. So if we had chosen transistors with an early voltage of 50 volts as opposed to transistors with an early voltage of 5 volts, we would actually see that we're operating at about 90% the maximum value that our output voltage, or excuse me, output resistance could ever have. Okay, so there are ways to maximize our system. All right, so now I want to talk about what are called false cascodes. So these are simply things that look like cascodes, but do not have that behavior. So let's say that we have an NPN current source, and it is degenerated with a PNP current source, where this is Q1 and this is Q2. Here's our output resistance. And let's consider the other side of this story. Which would be an NPN transistor acting as the degeneration source of a PNP current source. Q1, here's Q2. All right, so these fundamentally look extraordinarily similar to what we've just done. The only real change is that for this guy on the left, instead of degenerating by the same type of transistor, we've degenerated by the opposite type, okay? What does this do fundamentally? At a small signal level, what's the difference between these circuits? Or what's the difference between these two circuits and what we previously talked about?
They're not of the same type of
Right, but what small signal change occurs because of that? So let's look at Q2 right here. Okay. So this is a PNP based device. So that means this is the emitter, this is the base, and this is the collector, right? At small signal, the collector and the base are at the same voltage, which means that this is a diode connected device. What's the resistance of a diode connected device? You guys remember? So R naught was the output resistance of a current source connection, right? Which was good. That's what we just had. Whenever we had a diode connected device, it was R naught in parallel with something. R naught in parallel with 1 over GM, right? So fundamentally, we are degenerating our current source stage by a very small resistance, which is exactly the opposite effect of what we are trying to do, okay? So it is very, very important that we degenerate our stage with the same type of transistor so that we avoid one of these diode connected devices, which lower our output resistance appreciably, right? If we did the math here, we would find with IC of 1 milliamp, beta is 100 and VA is 5 volts, just like all the other examples that we've worked out this far. Our output resistance here would be roughly twice R naught 1. So it does increase the output resistance to some effect, but it's even smaller than just using an actual small resistor to degenerate. Okay? So these are here specifically to trip you up and to do a bad job. You should never actually use these. Okay, I just wanted to talk specifically about why you cannot. So now, let's talk about cascading MOSFETs. This is going to be a little more straightforward because we don't have to deal with RPi messing things up. So if we have a MOSFET current source, generated by some resistance RE like so. Or an NMOS device.
It's not RE, is it?
Sorry, you're absolutely right. It should be RS. Thank you. My output resistance is given by 1 plus, excuse me, GM-RS times R naught plus RS, which is the same thing as 1 plus GM-R naught times RS plus R naught. Those two relationships are interchangeable. Okay. So obviously, we look at this bottom guy right here, we can see that degenerating our current source with a fixed value resistance RS increases the output resistance by a factor of 1 plus GM R naught times the RS that we choose to degenerate them, right? Fairly straightforward. Well, as you can imagine, we're going to run into that same problem of a trade-off between headroom and output resistance, right? Because we need our device to be operating in the saturation region in order to get the largest possible GM out of it. So we can cascade MOSFET transistors as well. I had you guys kind of do this on one of your homework sets last quarter. So we could have an NMOS transistor M1 being degenerated by a second NMOS transistor M2, like so. Here's V bias 1, V bias 2. Or a PMOS transistor being degenerated by a PMOS transistor. Here's M1, here's M2. Just as a heads up as to what I'm doing, I'm always considering the cascode or degeneration transistor to be the second one and the principal current source one to be the first. So this is bias 1, bias 2. And in either case, our output resistance is R01 plus R02 plus GM1 R01 R02, which is approximately GM1 R01 R02, as we saw in 335. So let's wrap this talk up here with a brief example problem. Let's say that we have a simple MOSFET current source where our drain current ID is 200 microamps. UNCox is 100 microamps per volt squared. We have an aspect ratio of W over L is equal to 10 by 2. And a channeling modulation coefficient of lambda is 0.1 per volt. Let's calculate the output resistance by itself. When it's degenerated with a resistance RS is equal to 2 kilo ohms. And finally, when it's cascoded by an identical transistor. So current source, oops, I'm kind of running out of room here, apparently. To make things happen. All right, so by itself, we know that R naught 1 should be 1 over lambda ID. Somebody throw that into a calculator and tell me what we get. $50 kilo ohms. Wonderful. Okay. I agree with that wholeheartedly. Now let's see what happens when we include a 2 kilo ohm degeneration resistance. So I'm just going to write this as 50 kilo ohms. We'll need to know what GM is. So GM is square root of 2 mu n Cox W over L times ID. You've been given all of these parameters. I get 447.214 millisiemens for GM. So if I plug R01 and GM into this expression up here, what I get is 96.721. My stylus will write kilo. So we effectively doubled the output resistance by including that 2 kilo ohm resistor. Now, lastly, we just need to figure out effectively what GM times R naught squared is, right, using the substitution rule. So it's GM times R naught squared. .447 times 50,000 times 50,000. What do we get? 1.118 mega ohms. Thank you, Julia. That's a pretty significant increase in output resistance, right? Cascode MOSFETs are kind of the gold standard for boosting your output resistance to get yourself a good gain. So speaking of using a large output resistance to give us a good gain, let's now talk about the legwork required to analyze a cascode amplifier. All right, so we're probably not going to get to the analysis of cascode amplifiers today because we need to do something. So let me just draw what a picture of a cascoded amplifier is going to look like to explain why we're not going to go with just straightforward analysis, okay? So for a BJT version, that would look something like this. We have an ideal current source used to bias this amplifier. We'll talk about why we want it to be as close to ideal as possible, but the reason should be fairly obvious. And then we have a cascode configuration of bipolar junction transistors, where in this case, we're using NPNs. And what we do is we apply the input voltage Vin here. So let's call this Q1. So we apply the input voltage at the base of transistor Q1, and we take the output voltage at the collector of transistor Q2, where Q2 is biased as a current source. So we can kind of think of this in two ways, okay? We are either loading a common source amplifier with an active current source, and then taking the output here. Another way to think about it is that we are degenerating a common gate amplifier with the secondary amplifier stage. Gives a 6 of one, half dozen of the others, effectively the same thing, okay? A straightforward analysis of this circuit can absolutely be done using the techniques that we developed in 335. However, it is pretty damn rigorous because we've got this combination of transistors, right? In 335, all we had were effectively single transistor amplifiers, in as much as we applied the input to one pin on a particular amplifier. We took the output at a different pin of that same amplifier. Here, we're applying the input to Q1, measuring the output at a pin of Q2 that is not shared between the two. That makes the analysis a bit more of a pain in the butt. So what we are going to do is we are going to develop a more generic means by which to determine the gain of any amplifier circuit, okay? And that involves the concept of what's called short circuit transconductance. This method, by the way, can absolutely be applied to any single transistor amplifier as well. It's just not necessarily needed or useful for such simplistic circuits, okay? So in our analysis of transistors, we defined transconductance as the transistor's ability to generate an output current due to a small change in its input voltage. So for BJTs, that definition was GM is the derivative of IC taken with respect to voltage VBE, or simply IC over VT, where we are assuming forward active operation. And for MOSFETs, we actually had multiple different definitions for saturation, but we'll just stick with one. So the derivative of ID with respect to VGS, which we found to be the square root of twice UN Cox W over L times ID. We can generalize this transconductance relationship for literally any linear circuit, okay? So let's say that I have a black box linear circuit like so. What I am doing here is I am short circuiting the output terminal. I am applying a voltage Vn at the input terminal, and I am measuring a current I out that's flowing into the output node, okay? Our short circuit transconductance, capital GM, is simply the ratio of I out to Vn when our output voltage is forced to be 0 volts, or we short circuit our output. This is why it's called a short circuit transconductance. The concept of short circuit transconductance represents the circuit's ability to convert an input voltage into an output current, and it allows us to approach the concept of voltage gain from a different perspective. So what I mean by that is that, let's say that we have a black box. Like so, and it contains a simple amplifier circuit. So here's where we're measuring our output. Here's where we're applying our input, like so. And for the sake of argument, we'll say that V out and V in are measured with respect to ground. We can replace that network inside the black box with a Norton equivalent circuit because it's a two-terminal linear network. So that would be simply this representation. Where we have a current I out in parallel with a resistance R out, and we generate an output voltage V out that is equal to negative I out times R out. Since I out is simply GM, our short circuit transconductance, times V in, that gives us V out is equal to negative GM V in R out, or alternatively, our voltage gain is simply V out over V in is equal to negative capital GM, which is something effectively that we observed in an awful lot of our amplifiers, our single stage amplifiers last quarter to begin with. Our output voltage was usually related to our output resistance multiplied by some factor over and over and over again. So let's work an example that shows the efficacy of this method. And this will be the last thing that we do for today. So let's say that we have a common base amplifier. Yes. Absolutely. Sure.
So like we call our gain R V out over V in.
Mhm.
Do you have any name for R out over R?
Not that I'm aware of. So gain is V out over V in for voltage amplifier, right? So we've specifically defined it for a voltage amplifier to be V out over V in. But in some circuits, we might have what's called a transconductance gain, which would be I out over V in, or we might have a transresistance gain, which is V out over I in, or we might have a current gain, which is I out over I in. It just depends on the type of amplifier that we're dealing with. In this class, to this point, we've focused pretty strictly on voltage amplifiers, but I would argue that all of our transistor amplifiers are actually could be thought of as a two-stage amplifier where we have a transconductance amplifier and then an output stage, which is usually just a resistance. And that transconductance GM is a measure of our transconductance gain because it's literally how well or how efficiently I convert an input voltage to an output current, and then I make that output current flow through a resistor to convert that output current into an output voltage. We'll talk about that concept a lot more when we get into feedback amplifiers at the end of the course. Yes. Exactly right. AV means voltage or voltage gain. A is gain, V is voltage. I may not have mentioned that in this class or 335. I usually bring that up when we're in 223, and then I guess I just assume that you remember it for a year with no other introduction to it, which is probably not the best thing to do on my part, but it is what it is. Donald, were you raising your hand a moment ago, or are you good to go? Okay. All right, so let's look at a common base amplifier and do it, quote unquote, the hard way. All right. So here we have VCC with some resistance RC. We're taking our output voltage at the collector pin. We are applying our input voltage at the emitter. And then we have a bias voltage, which I'm just going to call VDC because I'm not giving myself enough room to write the word bias for whatever reason. Okay. So what I would like for us to do is to calculate the voltage gain of this circuit, including early effects, which I do not believe that we did in 335 because it was deemed difficult, right? So our small signal model for this circuit should look something like this. Since our base is tied to a DC voltage, it is at AC ground. Here we have our resistance R pi over which a voltage drop VBE occurs. Here is our emitter terminal. There is an input voltage being applied here. So here is VN. Here we have our dependent current source of GM VDE. In parallel with that dependent current source is our resistance RC, excuse me, lowercase r naught, getting ahead of myself, my apologies. And then out here is my resistance RC. And this is my output voltage terminal, where the output voltage is simply the voltage drop over resistor RC. So are we okay with my small signal representation? Nothing seems particularly wild or crazy, I hope. Okay. All right, so we can say that my output voltage V out is RC multiplied by this current that I am drawing here directly. So it's flowing into the negative polarity terminal and out the positive polarity terminal. So, and this current obviously splits up. One portion of it is GM times VBE, and the other portion of it is V out minus VN divided by R naught. So I'm just using Kirchhoff's current law to quantify this current. Sorry. So we have RC multiplied by, excuse me, negative RC multiplied by GM VBE plus V out minus Vn over R naught, like so. Let's see here. What else can we see? Well, the negative polarity terminal of VBE is associated with the positive polarity terminal of Vn. The positive polarity terminal of VBE is associated with ground, which is associated with the negative polarity terminal of Vn. So I can see pretty easily that VBE is negative Vn, right? So that's going to give me RC times GM times Vn plus Vn minus V out over R naught times RC. Where this negative sign being applied in here lets me flip the order of my subtraction. What I'm going to do now is put all my output terms on the left-hand side, all my input terms on the right-hand side. So I get V out plus V out times RC over R naught is equal to, sorry, that was my knee, Vn multiplied by VMRC plus RC over R naught. And from this, skipping a little step of algebra here where I'm just factoring out V out from the common terms on the left-hand side, what I get is my voltage gain, my pencil will write, is GM RC plus RC over R naught divided by 1 plus RC over R naught, which is the same as GM RC R naught over RC plus R naught plus RC over RC plus R naught. And you'll see why I wrote it in this very specific form momentarily. Okay. So this is method one. This is how we did things in 335. We get this answer. Nothing particularly wild or crazy here. Method number two, I'll do it on an entirely separate page to keep separate. Step one, we're going to calculate R out. So for this circuit, our output resistance calculation is going to look like this. Here's our base, here's our pi, here's VBE. Remember that when we are measuring our output resistance, we short circuit our input signal, so that's why our emitter is directly shorted to ground. Here's GM VBE in parallel with R naught. Here is our collector emitter terminals respectively. Here is RC, here's ground, here's the terminal into which we are trying to determine our output resistance. So somebody tell me what R out is here by inspection. RC in parallel with R, 100%. Didn't require a large amount of effort there by any shape or form, right? Step two, is to calculate our short circuit transconductance. So to be clear here, we are going to short circuit our output terminals and then find the current that's leaving that output terminal. Our circuit that we are analyzing is this guy. Here's R pi, here's VBE, here's VN, here's GM, VBE, here's R naught, here's RC. We are shorting the output terminal, and then we are trying to find this current I out. And capital GM is simply I out over V. So no current is going to branch off and flow through RC because it's grounded on both sides, right? So that's a pretty fantastic simplification. So what we can say is that I out is equal to GM VBE, right? So that's the portion that branches off and flows this way. And then we're going to have 0 minus VN over R naught. So negative VN over R naught. Well, what's the relationship between VBE and VN here? Donald. Mr. Martin, since I think you might go by Edward or something like that, I found out. Somebody, Logan maybe told me, email or something? I don't know. What do you actually go by?
I go by Edward.
Okay, Edward. After 3 years of me calling you the wrong name, how do I get VB, and what's the relationship between VBE and VN? Yes. Please help them out.
They're equal and opposite.
There you go. Thank you, whoever that was on Zoom, right? So they're the same voltage because they're the voltage measured between this point and ground. So this point and ground and this point and ground are the same thing, but they have the opposite polarities. VBE is negative VN. So what I'm going to do is I'm going to replace this VBE with a VN like here and put a negative sign there. Are we okay with this? Therefore, capital GM is simply negative GM plus 1 over R naught. Are we okay with that? From this, step 3 is to calculate our voltage gain, where our voltage gain AV is negative capital GM times R out. So that is, writing it this way, 1 over R naught plus GM times RC in parallel with R naught, which looks like RC R naught over RC plus R naught. And what this gives me is RC over RC plus R naught plus GM RC R naught over RC plus R naught, which is literally the exact same answer that we got when we worked it the hard way a few moments ago.